Today, we're going to dive into a brilliantly clever mathematical trick. It lets us find the rate of change, things like speed, growth, or reaction rates, for those times when we don't have a perfect formula to work with. And let's be real, in the real world, that's pretty much all the time. So picture this. You're tracking a car, and you want to know its exact speed at the very instant it passes a certain mark. Sounds simple enough, right? But what if you can't actually measure its speed directly?
What if all you've got is a list of its positions at different times? You know where it was at second 1, second 2, second 3, and so on. But how in the world do you pull the car's instantaneous speed out of just a list of locations? And that right there, that gets to the heart of the problem. Your classic calculus class is awesome if you have a perfect, neat equation, like f of x equals x squared. But out here, in science, in engineering, in finance, we almost never get clean equations. What do we get? We get data, we get measurements, we get a bunch of points on a graph. So what do? Well, we turn to this really powerful idea that, honestly, feels a lot like a super sophisticated version of connecting the dots. It's called numerical differentiation. Now, the formal definition is that it's a process for finding the derivative, and don't let that word scare you. That's just a fancy math term for a rate of change or a slope from a set of separate, discrete data points. This is the exact tool we need to solve our car problem and a whole lot more. The concept itself is surprisingly simple, and frankly, it's just beautiful. First, you take your data points. Easy enough. Second, you use a technique called interpolation to basically draw the most likely smooth curve that goes perfectly through all your dots. And third, once you have that curve, you can use regular old calculus to find its slope, its steepness at any single point you care about. It's really that elegant. Of course, it's not just random guessing. Mathematicians have come up with very specific tools to do this curve fitting and slope finding with incredible precision. The trick is just knowing which tool to grab from the toolbox for your particular set of data. And usually, the choice is pretty simple. If your data points are all spaced out nice and evenly, like you took a measurement every half second on the dot, you'll use something called a Newton-Gregory method. But if your points are all over the place, say you have measurements at 1 second, then 2 seconds, then you skip to 7 seconds, you use a different tool, like Newton's divided difference method. Just think of them as different specialty pencils for connecting the dots, one for perfect patterns and one for more chaotic, real-world data. Okay, this is all great in theory, but let's actually see it work. Let's grab some actual numbers from our source material and find out if this whole connect the dots trick really holds up. All right, here's our data. The x values are inputs, the f of x values are our outputs. Now you'll notice the x values are all spaced perfectly evenly, just a half unit apart. Our mission, should we choose to accept it, is to find the exact rate of change, the slope, at that very first point, where x is 1.5. So we take our data, we apply the right tool for these evenly spaced points. In this case, it's the Newton-Gregory forward method. We run the numbers, and the math gives us a single precise answer. The slope at x equals 1.5 is 4.750. But wait a minute, I know what you're thinking. A crucial question pops up, right? We just basically drew a curve to fit some dots. Isn't this just a fancy guess, an approximation? How can we possibly know for sure if 4.750 is the exact right answer? Well, this is the really cool part. It turns out those data points weren't random at all. As the source material reveals, they were secretly generated from a known function. F of x equals x cubed minus 2x plus 3. So now that we have the original formula, we don't have to guess anymore. We can use traditional calculus to check our work. The derivative of that function is 3x squared minus 2. And guess what happens when we plug our value, x equals 1.5, into that formula? We get exactly 4.750. It's a perfect match. Not close, not an approximation, it's identical. The answer we reverse engineered from just a handful of data points is the very same one we get from the actual formula. So the takeaway here is huge. This numerical method isn't just a guess, it is a remarkably accurate way to find the truth that's hidden inside your data. But you know what? Finding the speed of something is really just the beginning. This same core idea, finding the slope from data points, can be used for something even more powerful, finding the absolute highest or lowest point of a curve. Just think about it for a second. At the very top of a hill or the absolute bottom of a valley, the ground is momentarily flat, right? The slope is 0. So if we can figure out where the derivative, the slope, is equal to 0, we can find the peak. the maximum or the minimum value. So let's look at another set of data. And this time, notice the points are unevenly spaced. We've got values at x equals 1, then 2, then we jump all the way to 7, and then 8. You can see the function goes up, and then it comes back down. So somewhere in the middle there has to be a peak.
And check this out. We use the right tool for this messy, uneven data, Newton's divided difference method, and we analyze these 4 little points. The method tells us that the slope hits 0, and therefore the function hits its maximum value, precisely at x equals 4.5. We just found the peak of the mountain without ever seeing the whole mountain range.
And this isn't just some abstract math problem. This is huge. This process of finding the peak is called optimization, and it is the secret engine behind so much of our modern world. It's how engineers squeeze every last bit of efficiency out of an engine using test data. It's how businesses pinpoint their peak profit margins from sales figures. It's how designers create the most aerodynamic shapes you can imagine, all based on simulation results.
So I'll just leave you with this thought. What other complex problems, in medicine, in climate science, maybe in your own line of work, could we solve if we could reliably find that hidden peak, that point of maximum efficiency or greatest effect, all from just a handful of carefully chosen data points? The possibilities? Well, they're pretty much endless.